Thanks for the introduction, and good afternoon, everyone. I'm Stefano Di Matteo from CA, and this is VASCO, our ASIC test platform for cybersecurity, but specifically for hardware security on the FD-SOI technology. This is an initiative completely developed by CA that allows us as a researcher to test, to prototype, and to characterize the latest innovation in hardware security directly on the silicon, on the chip. But why hardware security? Okay, I know everyone knows the importance of the hardware for the security. The hardware is at the basis of the security chain. The hardware is like the root of trust of the security chain, and obviously if the security of the hardware is compromised, the security of the whole security chain will be compromised as well. Because the hardware enables some security procedures that are very important, like secure boot, authentication, encryption, and so on. That all depends on hardware and on the security and trustness of hardware. And this is obviously critical for a lot of sectors like healthcare, defense, IT, and so on. But today, the securitization of modern hardware component is challenging. It's challenging because of different reasons. First of all, the security threat. We have a lot of security threat today, starting from the quantum computing. We know that the classical crypto is not secure. We have post-quantum cryptography now, but post-quantum cryptography is not resistant. It is very difficult to protect against side-channel and fault injection attacks, for instance, that are attacks that exploit power consumption, timing, electromagnetic emission, hardware faults, and so on, to extract secrets. And these attacks today are also enhanced thanks to the help of the artificial intelligence. At the same time, this security standard and certification for security for the hardware evolve very fast, constantly, and because the new threat demand a continuous update to the security framework, but this put a lot of, let's say, pressure to the hardware designer and on the hardware manufacturer. At the same time, finally, we have some technological advancement that we want to exploit. Post-quantum cryptography, the RISC-V, and all the open hardware that allows to have more flexibility, but new things can bring security risk. And also we concentrate on FD-SOI technology that we think is a technology that is very good for embedded systems, thanks to power and energy efficiency and resilience against fault injection. And for this reason, we have VASCO in CA, which is, as I said, an ASIC platform for research and innovation in hardware security on the FD-SOI technology. The main objective of VASCO is to test hardware and software innovation directly on the silicon, to test the capabilities of the FD-SOI technology for resilience against side-channel attacks and fault injection attacks by the intrinsic resilience of this technology, and try to anticipate the migration to the FD-SOI technology for embedded systems. Thanks to VASCO, thanks to the silicon, to this platform, we do also digital twin. So we use hardware to build models. And that's the case of entropy sources for TRNG, because, as I said, the specification and the standard evolve very fast. And now, today, for the TRNG, we need a stochastical model. And thanks to VASCO, thanks to this platform, thanks to the silicon, we are able to develop stochastical models for entropy sources thanks to the silicon. But in general, with VASCO, we build security components at different abstraction levels, start at all the abstraction levels, starting from the software. We design secure protocols, secure software implementation of post-quantum crypto, and after we move at RTL level with the design of RISC-V processor, starting from classical RISC-V implementation, and improving the resistance against microarchitectural leakage. And we design secure hardware accelerators for PQC with countermeasure against side-channel fault injection attacks. We do the same for random number generators, because we design oscillators and we evaluate, we do stochastical model on the silicon. And finally, we work also at the lowest level of the abstraction level on the technology. Because, okay, we do all this assessment on the technology, on the FD-SOI, and we try also to build countermeasures that are based on the opportunity that this technology gives to us. In this slide, we have on the left side the roadmap of VASCO that started in 2018, and this is a simplified architecture of VASCO 2 that was taped out in 2022. And okay, some of the innovation that we put in VASCO, we have a this is a system on chip based on 32-bit RISC-V, but the RISC-V, the pipeline of the RISC-V is hardened versus fault injection attacks, thanks to some techniques like homomorphic integrity tags, dummy instruction, masking of the coding stage. We have innovation also in computational. We have a computational RAM. We adopt near-memory computing for the acceleration of post-quantum cryptography. We have dedicated accelerator for post-quantum cryptography with hybridization, so pre and post-quantum cryptography, with, again, countermeasure against a channel and fault injection. And we have the first ring oscillator based on TRNG characterized on this kind of technology. And here some scientific results that we achieved thanks to VASCO. So fault injection countermeasure on the CV32A40P processor, the noise characterization, the jitter noise characterization on ring oscillator that, as I said, allow us to develop stochastical models for ring oscillator, and hardware accelerator with countermeasure for fault injection for crypto, with pre- and post-quantum crypto, and near-memory computing applied also to cryptography. To conclude, this is a preview of the latest release of VASCO that we taped out in April 2025, so last month. And in this case, we extended the capabilities of VASCO 2. In this case, we have an application tile with CVA6 processor enhanced against fault injection attacks. And on the right side, we have the embedded tile with 32-bit RISC-V processor. On the red part, on the right side of the architecture, we have accelerators dedicated to post-quantum cryptography with countermeasure against channel attacks based on masking. And in this case, we designed dedicated accelerator for different tasks that are required by the latest standard for PQC, the MLCAM, based on Kyber. We proposed a new architecture for TRNG based on Aero, Moore, and COSO, and we are going to do, again, stochastical models for this kind of TRNG. And on the left side of this figure, we have also a test tile completely dedicated to the assessment of the FD-SOI technology and to assess the countermeasure for side channel attacks with IS scores and resistance against laser attacks on memories. Thanks for the attention, and if you have any question, we are happy to answer at the stand of the CA. Thanks.
Thank you so much.